when we work with sets that are of the same type of element, then we can combine them using operations that'll look very familiar, very similar to the logic operations that we talked about earlier with propositional logic. So to use these operations, we have two sets, A and B, where the type of elements in the sets are the same. So the way we say that is we say that both sets are taking elements from a specified universal set. We use the letter U just to stand for the universal set. So in some problems, the universal set will be the integers. In some problems, the universal set might be the set of all students at the college. The universal set is just a set of objects of the same type. And then our A, B, C, whatever sets we build, we know that the elements are of the same type. And so with that in mind, then when we define operations called intersection union and set subtraction or set difference, and you'll notice the symbols look very similar to the ones we used in logic. So for example, A intersect B, we use this symbol. It looks like a rounded version of our AND symbol, and that is actually what's happening. You're in a set A and B if you're in both the sets A and B. So if you're in both sets, then you're in the intersection of the two sets. The union symbol looks like this. It looks like a rounded version of our OR statement, and that's exactly what it is. You're an element of A union B if you are either in A or B. And once again, that is an inclusive OR. The set subtraction is a little different than we've seen with the logic symbols. It's very common in abstract mathematics courses or upper level classes that use mathematics. So it's here. A minus B means the set of all the things in A which are not in B. We think of that as sort of the throwaway operation, meaning we start with a set A and we throw away anything. In other words, we remove anything that's also in B. And so that leaves us with things that were originally in A, but were not also in B. And then if we do set subtraction where we're subtracting from the universal set, so we start with the universe and subtract a set A, then we just write that as A prime or A complement of A, and that does correspond to our logical not. So these logical symbols, the intersection corresponds to logical and, the union corresponds to logical or, and the complement corresponds to logical not. The set subtraction is just a special case of using the complement. So it is a common set operation, but it doesn't have a corresponding single operation in our logic world. So let's do some practice with these. Here we have some sets that are chosen from the small universe of just the numbers from 1 to 10. And they all have a little bit of structure to them so that it's easier to think about what you're doing. It doesn't seem random. So A are the odd numbers, B are the even numbers, C are the prime numbers, and D are just the bigger numbers. And so that we can kind of get our head around what they're each saying. And then we can do each of these operations. So let's do a couple first. Then I'll talk to you about how to do something more complicated, and then I'll show you the answers you can check. So let's practice each of the basic types. A intersect C means everything that's in A and in C. So when we see the intersection, we should think and. So I'm looking at the sets A and C. So here's A, here's C. I want just the elements that are in both. So the elements that are in both are 3, 5, and 7. Those are the only elements that are in both A and C. For the union operation, my example number 2 there is B union D. And so again, I go locate my B and locate my D. And I would like everything that's in either B or D. So the easy way to list those is to just write down everything that's in one of them. So I'll just write down everything that's in B, because those are all there for sure. And then I'll look at D and say, who else do I need? 6, 8, and 10 are already in my set, already listed, so I only need 7 and 9 to get the rest of them. You can see how when I do it that way, my numbers don't end up in order, and that's why at the beginning of this unit I talked about the fact that the order of the elements within the set doesn't make any difference, and it's not that unusual for a set to arise where the numbers aren't in any particular order. The set subtraction operation, number 3, says B minus D, and so that's the same two sets, so I'll leave them underlined, but that's supposed to mean everything that's in B that's not in D. So I should look for each element of B and ask myself, is it also in D? So this one, element 2, is not also in D. so that would be included. 4 is in B, but not in D. 6 is not. 6 is in B, but it's also in D. So is 8, so is 10. So the only numbers, the only elements that are in B, but not in D, are 2 and 4. So notice how that had the effect of taking set B and just throwing away anything that was also in D. That's essentially what I'm doing there. So the set subtraction is just a throwaway operator. You're saying start with one set and then just toss out anything that occurs in the other one. And then finally, B complement is there, and again, that's really just shorthand for the universe minus B. And of course, we already saw that B was the even numbers, and so the universe here, 1 through 10, throwing out the even numbers, is just going to leave you with the odd numbers. And so I could list those, but it also has a name. In this case, we happen to have given that the name A. Now, when we're doing operations where we have parenthesized expressions, we really do the same thing that we do in algebra and arithmetic, which is work inside the parentheses outward. So let me just use as an example number 6, because I have more room to write there. So if I'm working on number 6, the parenthesized expression I need to figure out first. So as a partial step to write the answer for number 6, I would just want to write down what the thing in parentheses is first. So A union C means this set union this set. So in other words, everything that's in one or the other. So like before, I can just write down what's in one of them. 1, 3, 5, 7, 9 is in A. And then look at C and say, who did I miss? I only missed 2. So A union C looks like that. And so now I know what this A union C looks like. And now I can say I want to know everything that's in there and in B. So now I'm past this. So now I'm looking at the intersection of these two sets. In other words, what do these two sets have in common? And if I look at them, it looks like only the number 2 is common between those two sets. So this would be the set with just the number 2 in it. And so that's what we would do for all of these where we have to kind of build them up. So in the number 7, you might write on the side B complement and C complement separately, and then look at what's in common. For number 8, you might do B union C first, and then take the complement. So I'll just do that since I have room to write here. B union C would be everything that's in B or C. So that's 2, 4, 6, 8, 10. That's what's in B. And then C would throw in 3, 5, and 7. So actually got quite a few things there. But then I want the complement of that. So the complement, that's almost all the numbers, 2, 4, 6, 8, 10, 3, 5, 7. The only thing I didn't mention was 1 and 9. So the complement of the set 2, 4, 6, 8, 10, 3, 5, 7, the complement of that is just the set 1, 9. Now, if you finish these, you'll notice a couple of things. One of them is that this number 7 is also 1, 9. So these are actually the same thing. And if you think about the logic of what they're saying, that's not too surprising, because in this set, we're saying you're going to be in here if you're in if you're in B or C, but then we want the numbers that aren't that way. So we have the complement of them. So the negation of being in B or C, we know from De Morgan's law for logic, the negation of being in B or C is being not in B and not in C, and that's exactly what this says. So De Morgan's law for logic also applies to sets. You can think of it as an algebra rule that when you have the complement outside the parentheses, the complement can be distributed, but the consequence is that your or changes to and. So there is a version of De Morgan's rule or De Morgan's law that applies to set operations for exactly the same reason that it works for logical operations. The other thing I'll point out to you is that this last statement, B intersect D prime, is exactly the same as this. If you say out loud what they mean, you'll see that. This means everything that's in B and also not in D. This means everything in B, not in D. So these two things mean exactly the same thing. This is what I meant about the set subtraction not really being necessary. If you wanted to do set subtraction, you can do that very easily just using the intersection and complement operations that we already have. So if you'd like to take 5 seconds to pause the video and try working out the rest of these to compare answers, I'll put the answers up when I mentally count to 3. So these are the answers I got for these questions. If you have any questions with them, send me an email, or I'll bring them to class.